So here I'm going to talk about two other vectors. We already have one vector. So here's a space curve. And the one vector that I'm talking about is we can already take the derivative of that, and I know that that vector is the tangent vector. So that's our r prime. And if I divide it by its magnitude, we can get our unit tangent vector. So this is the tangent vector, the derivative, and we can get our unit tangent vector. So we have from previous then our unit tangent vector, which is just our regular tangent vector divided by its magnitude. So that would be this 1 unit long. So let's divide this by its magnitude. I'm going to erase this part here. And so that's the unit tangent vector then. I've already divided out by its magnitude. And we talked about t prime when we were doing our curvature, the derivative of the unit tangent vector. And we proved that it was perpendicular to the tangent vector. So if I put in here t prime, it would be pulling this way. It can't, remember we made the argument where it can't increase the magnitude of t, it can't decrease the magnitude of t, it changes the direction of t, so it's only going to be perpendicular. There's t prime. And it might not be a unit vector. But if I want to make it a unit vector, it means perpendicular to t, it's normal to t, it's orthogonal to t. Perpendicular, normal, orthogonal, they all mean the same thing. The dot product is equal to 0. But if I want to make this a unit vector, that's what this is here. And you should all have vector hats on them. I'm dividing it by its magnitude. So now that's scaled down. That's also a length of 1. So I'm going to just move it over here. There's my normal vector. So I've taken the t prime and scaled it down. So this is 1 unit long, this is 1 unit long, and we know from previous that this is a right angle. So that's why we call this the normal vector, because it's perpendicular to the tangent vector. It's changing the tangent vector. That's why it's got the t prime on it. Just get rid of all. Now we're in 3D, let's say. So I've already got two vectors, 1, 2, and they're perpendicular to each other. If I had a third vector at this point, at this point that was perpendicular to the other two, I'd have like a 3D coordinate system, an x, a y, a z, but they would be not x, y, z, but it would be its own coordinate system, perpendicular, orthogonal to itself, and unit 1. So I need another vector that's coming, okay, I can't draw it, it's coming out of the page. So perpendicular to t and perpendicular to n. I need it to come out of the page. So how do I get a vector that's perpendicular to t and to n? Yeah, you cross product it. So b is the vector that's perpendicular to t and n. It's going to come out of the page. Now because it's perpendicular or normal or orthogonal, it's normal to both t and n. We call it the binormal because it's perpendicular to the two other vectors we have. So I get it by just taking the cross product of those two. Now, the magnitude of t is 1. The magnitude of n is 1. We make them unit vectors. What about b? Do we have to divide that by something to make it the magnitude? What's the magnitude of b? That's my question. Well, it's a cross product, so that would be magnitude of t, magnitude of n, that's an n, sine of the angle between them. But the magnitude of t is 1. It's the unit tangent vector. The magnitude of n is 1. We scale it. The angle between t and n is 90 degrees. So that's 1. 1 times 1 times 1, 1. So I'm saying that the b is a unit vector as well. The binormal vector just on its own has a magnitude of 1. So now I've got 3 vectors that are valued at that point. The tangent vector, the normal vector, and the binormal vector, which I can't draw because it comes out of the page. They're all unit vectors, and it forms a 3D coordinate system. What's the point of all this? Well, say that I was on, now the example that we always give is the same. Say I'm on a spaceship, which, yeah, happens all the time. So I'm on a spaceship, and I'm flying along this curve given by this, I'm on a spaceship. It's a space curve. I'm flying in space. But I have a coordinate system then that stays with me on my spaceship and doesn't change, right? If I'm going to draw a rocket. That's supposed to be a rocket. I'm on the rocket. T is always pointed straight up. N is always pointed perpendicular to T, but like pulling me in my direction, the direction that I'm steering. And B is always straight out of the page that way. So I've got a 3D coordinate system, and I can do things with the coordinate system. Instead of X and Y and Z, I have T and N and B, and that coordinate system moves with me. So I can calculate stuff that has to do with just me on the spaceship, moving stuff around the spaceship. If I'm, I don't know, 3D printing or throwing a baseball or whatever you do on spaceships. Anyway, a coordinate system, that's what it's for. And it's in 3D because we use a cross product. So lastly, we have what we're going to call the normal plane. So N and B, they define a plane at the point in the space curve. So if we're talking about that space curve, it pierces through the normal plane perpendicular, right? Because we've got our tangent vector would be normal to the curve, so piercing through. You've got would be piercing through, that would be T. You've got N, which is perpendicular to the T, and you've got B, which is perpendicular to them both. So once we define the plane as perpendicular to the tangent, you've got N and B, which then define the plane. All we need for a plane is 2 vectors and a point. So if I want the scalar equation of a plane, then just the t vector gives me the normal vector to the plane. But the normal to the curve in this case then is in the normal to the curve lies in the normal plane. Let's do our example. Here's our space curve. So at the point. So now let's get I need R prime. So taking the derivative, that's 1, 3t squared, and 2. So there's our R prime. I need the magnitude of that R prime. Because I'm building that t vector. So that's going to be equal to the square root of first component squared plus second component squared plus third component squared. So first component squared plus second component squared t to the 4 plus third component squared. And I want that magnitude at the point 1, 1, 2. What time is it at the point 1, 1, 2? At the point 1, 1, 2, t is equal to 1. So this magnitude then is going to be, when I plug t equal to 1 in, that's going to be root 14. So our t vector at the point that I'm interested in, our t vector is equal to the r vector when t is equal to 1 divided by its magnitude, which is root 14. Okay, so I need t prime, so I differentiated each one of these pieces with respect to time, and now I've got t prime, still as a function of time. Now I need that, I've done my differentiating of t to get t prime. I need this at the point 1, 1, 2, so t is equal to 1. So I'm taking my formula here, and I'm making t equal 1. So all of these brackets will be 14 and minus 18, 1 to the 3. That'll be 30 times 1, and this will be 14. So now I've got the t prime evaluated at that point. Now I need its magnitude because the normal vector is t prime made into a unit vector. So I need to get its magnitude. Magnitude, big square root, first piece squared plus second piece squared plus third piece squared. Let's simplify this up and see what we get. Oh, turns out to be not too bad. That's the magnitude of t prime. So that's going to let me make this into a unit vector. I have to divide each piece here. So I'm taking t prime and dividing each piece by its magnitude. Now this will turn into the normal vector. It'll have a magnitude of 1. So let's simplify each one of these pieces then. So now when I've simplified these, each one of these three components of the normal vector, here's our simplified normal vector. It should have a magnitude of 1, and it should be parallel to t prime, and it should be perpendicular. If it's parallel to t prime, it should be perpendicular to t as well. So I could check this by taking the dot product of n against t to get 0. I could take the dot product of t prime and t and also get 0, as we've shown before. But now I've got one of the vectors, the n. Now I just need the b vector. Here's a cross product. I have to take the t vector and cross product the n vector. So the binormal vector is the tangent vector, the unit tangent vector t, cross product with the normal vector, which is a unit vector. Here's the tangent vector. Now I don't need t's anymore. I've subbed in t equal 1 into everything. Now I just need to take this cross product. So when I take this cross product, there's the b vector. Now there's a lot of algebra that I did there that I didn't show you, which you can check. You probably don't want to go through all of the algebra, but let's think about how we can check to see if my b vector is right. The binormal vector is supposed to be perpendicular to t. If I dot product it against t, I do get 0. That's an easy check. It's also supposed to be perpendicular to n. So if I dot product it against n, I do get 0. That's an easy check. Lastly, we can take its magnitude, and maybe that's easier to do too. If I take its magnitude, it's this squared plus this squared, square root of whole deal, check that, that's equal to 1. Those are a lot easier algebra checks than redoing the whole calculation. Anyway, we've got our t vector, we've got our b vector, we've defined the normal plane. Let's finish that off by writing it. Let's write our normal plane then as, so p for plane vector, let's think, p for plane vector, that's going to equal to a point, and the point we were at was 1, 1, 2. Plus, now it's a plane, so two-dimensional, so k times one vector, let's say the t vector, plus, I need another letter, I don't know, h, times the n, times the b vector. Oh, wait, this is supposed to be the n vector here, right? Not the t vector. The t vector is perpendicular to the plane. I want the n vector. So it's the point plus some number times the n vector plus some number times the b vector. There's the vector equation of the normal plane, the plane that the curve passes through perpendicularly. If I wanted the scalar equation of that plane, I need the vector that's perpendicular to the plane, which is t. So, or any vector that's parallel to t. I don't want those root 14s. So the tangent vector, the t, I can just take the vector 1, 3, 2. So that'll be 1 times x plus 3 times y plus 2 times z is equal to, now I just need to know the value. I know that the point 1, 1, 2 is on there, so I plug 1 in, and 1, that's going to be 4 plus 4, 8. So there's the scalar equation. Vector equation of the normal plane, scalar equation of the normal plane. A caution, the normal vector to the plane is not the normal vector, not this n vector, but it's the little n from our vector equations and scalar equations of plane section.